Introduce myself briefly first. My name is Nikita. I work as a Rust engineer at MadeSafe. It is a company that develops the kind of peer-to-peer network technology, and almost our entire code base is in Rust. And actually, it's one of the biggest Rust projects out there, except for Servo, perhaps. Servo is certainly bigger, but we have like tens of thousands of lines of code in Rust, and we use FFI extensively in our work. And we use FFI to make our libraries usable from other languages like JavaScript and C#, and soon we'll be adding Java and Python and other languages to our stack. And today we want to share our approaches to dealing with FFI and structuring our APIs with you. And we learned these things in a very hard way because we have been developing our libraries for more than a year. And there are a lot of intricate details in FFI that you probably can't find in the Rust documentation, but you can find it in Rust no-mangle and in some like obscure pages in the Rust documentation. And I won't be sharing too many of these intricate details, but let's start with the basics. Like, what is FFI actually at all? Well, FFI stands for Foreign Function Interface. It is basically a way to talk to the external world, which unfortunately is not every single program in the world is written in Rust yet. But, exactly, we are working on it. So yeah, we have to talk to other programming languages, and we have to find some proper way, way to deal with the other programming languages and with the external world. So FFI in Rust can be considered as a standardized way to serialize your data and exchange it with other programs. And actually, it can be compared to HTTP and JSON in the sense that, well, HTTP is a networking protocol and JSON is a data serialization standard, but they are commonly used to expose your API from your library so that other languages and other programs can use it. And the main advantage of HTTP and JSON is that they're supported by a majority of language. It will be a very hard task to find a programming language that doesn't support HTTP or JSON in some form. And we at MadeSafe actually too used JSON in HTTP. It was structured like a library that started a web server that exposed a REST API. And that REST API was used by a JavaScript program, basically a desktop application, and it talked to the Rust library via the REST API protocol. But this approach also has its disadvantages, and the main disadvantage that we have discovered is at the point of time when we decided to start supporting mobile platforms like Android and iOS. And basically, there's no simple way to expose your API through the HTTP protocol on mobile platforms, because if you confine your library and your HTTP API to a single app, it will work, maybe on Android. On iOS, it might be a bit harder. But anyway, it's simple. But if you want to communicate between the applications, like if you have two apps and you want one app to talk to the other app that runs the web server, it will be very hard. You have to invent some peculiar ways, running your own custom VPN protocol just to talk to the other program and to send your HTTP request. And it's not easy, and we decided that to switch our approaches to FFI, basically. And FFI is based on platform-dependent C, Application Binary Interface, or ABI. And it's called platform-dependent because basically how it works. You can, if you compile your library if you compile your library on Linux, you can't reuse the same binary on other platforms like Windows or Mac OS. You have to recompile your library for these platforms because they use different calling conventions, and they're like very incompatible. It's not even that the system APIs are incompatible. They're incompatible on the lowest system layer. But at the same time, you can be sure that like all APIs, all libraries that follow the same C calling convention will be working on this platform. Like you can talk to any program, any other program that follows the same convention, and it will work. And it actually works on mobile platforms as well. C ABI and the C language itself can be considered as a kind of lingua franca of system APIs. And it's likely that you have used C library in your developer life at least once. And Rust also supports these conventions in the form of the Rust FFI libraries as almost any other language. So we can use this Rust FFI API to talk to any other language, basically. But at the same time, there is no single proper way to handle our FFI calls, because like it's like with any other API, you don't you don't have a single standard to structure your Rust API, for instance. You have to invent your own way and your own convention that to follow. There are only like patterns and best practices that we can follow, and I want to share the common approaches that we have found at our company, and that these approaches work for us, and like I want to tell you about them. And let's start with the simplest thing that we can find in our FFI API. That is a function. So how do we expose a function to the external world? Basically, as you can see, it's practically the same thing as you write your function in Rust. It's it's very similar to the rest of the functions, but you have to add some extra meta information to expose this function as an FFI function. You have to declare it public, because otherwise it won't make sense to make it module private. It won't make sense to confine it to a single module, because otherwise how would the external world will know about your function, right? So you have to make it public first. Next, you have to add the extern C declaration. And it basically tells the Rust compiler that it should make this function follow the C calling convention. And finally, that last bit, no-mangle, tells the compiler that it should also not mangle the function name. That is, it should not encode the function name in the way that only the Rust compiler will understand it. That's practically it for functions. But you also have to know another thing about FFI functions, is that you can't use Rust types in the function arguments and in the return types. Because Rust types are very implementation specific. Just to use the Rust structures from the standard library in other languages and to expose them in FFI, you basically would have to re-implement the entire Rust standard library in other languages, and you have to re-implement it with every single other new Rust version, because they're very dependent on the Rust compiler version, and they're very implementation specific. So what we can do is to use only the only types that are understood, that other languages understand, and we basically have access to only the numeric types, either integer or floating point. And we also can use pointers, which are practically can be thought of as numeric types as well, because if you compile your library on a 32-bit platform, a pointer will be just a 32-bit number, and correspondingly on a 64-bit platform it will be just U64. And of course, we can't deal with, only with numbers in our API. We have to structure, so we have to find some, we have to use some complex structures, like structs in Rust, for instance. But at the same time, structures themselves are different in Rust because we can't use the Rust structs as they are. They use different memory layout, and other C programs and other languages won't understand this memory layout. So what we have to do is to basically restructure these structures as C-compatible structures, and that's what that wrapper C attribute does. And we also can use only numeric types, pointers, and other C structures for the struct field types. And to make it C-compatible, we have to make sure that all fields in this structure are also wrapper C or the primitive types or pointers. And that way, we can tell the Rust compiler that by using this attribute, that it should make the memory layout understandable by the C programs. But of course, the available means to structure our APIs are pretty basic. And you might be wondering, how do we actually build any useful software when we have access to only to primitive numbers and pointers? But the thing is, we can combine all these basic means to structure our API in multiple ways. For instance, another way to deal with structures would be to use Opaque pointers. Basically, a pack pointer is just a black box that we provide a user. And user doesn't need to, a user is not concerned about the thing that this pointer represents. The user is not, they doesn't know about anything that is stored in that structure. The only thing that they should be concerned about is that they should store this value and provide it back to our functions, to our API. And we can dereference this pointer. And the main advantage of this approach is that we can use Rust structures as well, because the user doesn't know about the internal representation of structure, and we can basically represent any type of data. We just need to provide the user a kind of a black box. So this pointer is referenced only on the Rust side, actually. And all of that, what we have learned so far is pretty simple and basic until we get to the crucial question of ownership and borrowing, the concept that doesn't translate to other languages in a quite a straightforward way. Because how we can pass an ownership to an external program at all? What we can do is to put that value, for instance, if we have some kind of a structure that is a wrapper C struct, we can put it in a box and then convert it into a row pointer. And by converting it into a row pointer, you're basically telling the Rust compiler that you should forget about it, and the pointer lifetime will be effectively unlimited until you explicitly free it by yourself. So it becomes our responsibility to free this box. And we free memory just by converting pointer back to a box structure, basically. And when this box goes out of the scope, it will be automatically freed by Rust. That's why we have this underscore variable, because we don't care about what this box contains. We just need to dereference it, dereference the pointer, construct the box again, and when this underscore variable goes out of the scope, the box will be deallocated automatically by the Rust allocator. And for borrowing, that was about the transfer of ownership for structs and simple values. And for borrowing, it's a bit more straightforward, because for borrowing, we just can't convert a Rust reference to a pointer. Because essentially, all Rust references are pointers by themselves, because all the reference represents is just it points to some region of memory. So basically, by converting that reference to a pointer, we're just taking an address of that region of memory and like basically storing that in a variable or passing it down to some other program. And this is not even an unsafe code because all Rust references are essentially pointers, and we don't need to do any kind of transformation on it, or like we don't need to do anything special about it. Like we can just convert them into, we can even convert them to pointers implicitly. We don't need to write this as const native struct construct. We can just put a reference there, and it will be implicitly converted into a pointer by the Rust compiler. And now that we have dealt so far with simple structures and simple values and primitive values, and we need to somehow deal with sequences. And sequences are a bit more complicated, but they are, at the same time, they're simpler than structs because vectors in Rust are guaranteed to be stored in a contiguous memory, in the sense that they have values followed one by another. So if you look at this slide, we have a vector of 1 and 2, which are 32-bit values. But actually, they are represented in memory. They can be basically transmuted to a single 64-bit value, because these values are stored right after another. And this simplifies our task of talking to the external world, because we can just take this vector and pass its pointer to an external program, and we just need to care about the vector's length. We also need to hand over to the external world, because the vector itself doesn't contain any information about its length. Like, it's not stored somewhere in the memory, it's stored separately. That's why we need to pass it over as a separate variable. And basically, this thing about the contiguous memory applies to any type of a vector. Like, even if you have some kind of complex structure stored in your vector, if you have a sequence of complex structures, they will be stored as a contiguous memory as well. And the fact that vector memory is contiguous actually helps us in developing code in Rust, because it's very fast and efficient. If you pass it to an external program, all you need to do is to get an address of this vector, and it's like a very cheap operation. Ownership is a bit more complicated, however, because vectors have some implementation-specific details that we need to preserve when we hand the vectors over to external programs. Like, in particular, we need to have, besides the vector's length, we have to also pass the vector's capacity. And the capacity is, like, we can live without it in the external world. Like, the external world doesn't need to know about the vector's capacity, because it's a Rust-specific implementation detail in the standard library. But we can't get rid of it. We have to pass it to an external program, because otherwise we won't be able to get that vector back in our program when we need to free our memory. So basically what it means is that we need to preserve the vector capacity to tell the Rust allocator, to inform the Rust allocator about the full vector information, so that it can deallocate the entire vector when we get it back, when we get the ownership of this vector back. And you might have noticed that on the previous slide, we called that non-forget function. That might be a bit new to you, but it is a very important part, because we need to make sure that Rust will not deallocate this vector prematurely. So what no-manforget does basically is that it tells the Rust compiler to forget about that variable, about that vector, and to forget that this variable even exists in such scope. And in the fact that the Rust compiler forgets about it, it won't deallocate this variable when it goes out of the scope until we explicitly tell the compiler to do so. And after we have provided the user with the full information about the vector, and effectively we handed the ownership of the vector to the end user, we also need to provide the user with a means to deallocate it. And the simplest way to do that is to basically provide an FFI function that the user will call when he wants this vector anymore. This function should take 3 parameters, like in the very same way how we constructed the vector. We took the vector pointer, its length and its capacity. We need to provide the exact same variables when we deallocate it. And we basically call this a vector from row function. And we reconstruct the vector from this information. And then when it goes out of the scope, the Rust compiler will free it automatically. So the disadvantage of transferring ownership to an external programs is that now it's the user who is responsible for deallocating this memory to prevent memory leaks. And it's a very fragile concept because users are prone to forgetting about these things, and it's very easy to produce memory leak, to cause memory leaks because of that. And we have to be extra careful with transfer of ownerships. And as for taking values from the external world into Rust, it's actually a much more simple concept. We just need to have 2 variables, a pointer and the length of a sequence. We don't need capacity because we can derive the capacity from the length, and we can construct the vector ourselves. So we take the pointer and the length, and we convert it into a slice first. And then we can convert that slice into a vector by calling that toOwned function, which basically copies the memory. If we won't call the toOwned, the slice will point to the exact same memory region. And if this memory region is deallocated on the other side, then slice will point to an effectively deallocated memory region, and this will be undefined behavior. And actually, speaking of slices, we can export them too, and it's not too much different from vectors, but obviously we won't be able to export the ownership, to transfer ownership for slices, because slices themselves are basically borrowing of values, and they are basically just references. And we need to use a spatial construct like ASPTR, because we can't convert these references. If you remember, I said that references are basically pointers in Rust as well. But you can't convert your reference to a slice into a pointer, because slice pointers are fat pointers. They are not 64-bit or 32-bit, depending on your system. They actually contain 128 bits, because they also contain the length of the slice. So what we need to do is to use this either as PTR or as mutable PTR to take a pointer for a slice. Also, it's very important to make sure that the lifetime of your slice of the underlying sequence, either an array or a vector, is long enough, because otherwise, if your vector will be deallocated, then the slice will point to a dead memory region, and it will be undefined behavior all over again, which is not a pleasant thing. So strings. They're pretty much the same as vectors, because in Rust, strings are basically vectors of U8 bytes, and they just contain strings that are encoded in UTF-8. But we have to be extra careful when passing Rust strings to external programs, because they are not guaranteed to have no 0 bytes. So basically, what that means is that they are not compatible with the standard C string convention, which says that the length of a string is determined by the 0 byte at the end of that string. And in Rust, they're structured in a different way. They have a length of a string along with the rest of the information. So we can't just take a pointer of a string and pass it to an external program. We have to do some extra steps. like basically the same steps as we have applied to vectors. We need to take the pointer for a string, we need to take its length and capacity, and it's very important to preserve string's capacity as well as vectors. And freeing the memory is basically the same as for vectors. Like we just reconstruct a string from the raw parts that we get on the previous step, and when it goes out of the scope, it will be deallocated by Rust. But there are also several other different string types which are suited specifically for FFI purposes. And it's actually recommended to use them instead of Rust strings to talk to external programs, because these string types, like in the std FFI module, are more conventional. So both types, CString and CStr, correspond to the standard null-terminated string, and they will be. You can be sure that when you pass a pointer to a CStr or CString, they will be compatible with any way to work with strings and with other programs. So to construct a C string, which owns its memory region, just as the string struct itself, just call the constructor function CString new. And it will do a full memory copy of the strings that you have passed to it, and it will be deallocated when you want it to, like when you call when it goes out of the scope. The semantics of allocation and ownership are practically the same as with the standard libraries Rust strings. And borrowing and ownership of the C strings are much more easier than and much more straightforward than the standard Rust strings, because we can just basically take a vector of C string and pass it as it is. And if we want to pass ownership of it, we just convert it into a row pointer by calling that into row. And when we want to free it, we just reconstruct this string structure, and when it goes out of scope, it will be deallocated. And you might have noticed that this interface is pretty much similar to what we have seen already with boxes and structs. And it works essentially the same, and it follows the same convention from the Rust standard library, even with the same function names. And the counterpart type, CStr, which has semantics that are very similar to reference to a string in Rust, that %str thing. So it doesn't own any memory by itself, and it can be converted into a Rust string reference in a very straightforward way by calling the toStr function. And then, of course, you can convert that reference to a string into a string by calling toOwned, which will copy memory and hand the memory ownership to the string. But creating a CStr is unsafe. You have to be extra careful you have to be careful to provide a valid C string that is null terminated, because otherwise, if you provided an invalid pointer or a pointer to not a valid C string, it will be undefined behavior again. And so far, we have converted the basic. We have covered the basic types, structures, sequences, and strings. And so let's get back to a bit more complicated topic of borrowing and ownership. And borrowing values from Rust is a bit more complicated task, because we can't ensure that the lifetime of values which we have borrowed it's not guaranteed to that this lifetime of these values will be indefinite. Because for instance, imagine how you would pass such borrowed pointer as a return value from a function. So when this value goes out of the scope of this function, it will be deallocated automatically by the Rust compiler. And now when the pointer to this value gets to your external program that uses your Rust library, it will be like invalid memory. So how do we deal with that even? Well, this is an especially hard task when you deal with garbage collected languages like JavaScript. And You might think that this can be alleviated by transferring ownership, but it's not actually simpler because a user will always have to care about deallocating memory, and this is very easy to produce memory leaks. And it's very easy to lose track of which memory regions you are already allocated and which memory regions you deallocated, and it's usually up to user, and we can't affect it in any way. So it's a user's task, and it's not good because it's much better to if it's us who care about the memory. So at MedSafe, we have encountered multiple cases of memory errors and undefined behavior related to borrowing and ownership. Because it's really hard to write unsafe code in Rust because we don't have the Rust compiler guarantees, and we constantly bumped into segmentation faults and memory leaks and memory errors, all kinds of them. So we have decided to learn more ways of structuring our APIs, and we considered several other options. So what we have decided to try is to structure our APIs around callbacks. It is kind of an unconventional way, but basically we use callbacks to pass all data to external programs. And it simplifies the task a lot if you look at the implementation of this callback thing. Because we basically pass the pointer and all relevant data to user's callback as the callback arguments. And when the execution thread gets back to our function, like the Rust func, when the execution thread gets back to it, it continues the execution, and then the vector goes out of the scope, and then it's dropped, and the memory is deallocated automatically. So a user doesn't need to deal with memory allocation in any way. They don't need to like deallocate memory or care about it at all. The only disadvantage of this approach is that user will have to make a copy of the entire data. A user will have to copy all variables and all structures that we pass to them. And it's not a big deal if we work with small structures and small data types or small vectors, but it won't work that great for vectors that contain several megabytes of data, for instance. And for heavy vectors, we can combine the callback approach with the ownership transfer and make it a user's responsibility to deallocate large values. So it's like there is no single answer and there is no single way to structure APIs, but we can combine several approaches. And this way, when we are using callbacks, there is an advantage that we can also automate the allocation for our C structs. So for instance, if your C if your structure that is marked as C wrapper, if it contains a vector or a string fields, you can deallocate them just by implementing the drop trait, which basically consists of just a single function that is called when your structure goes out of the scope. And the recent addition to the Rust compiler is very nice that we are now able to implement the drop trait for wrapper C structures as well. And luckily, when we deal with this callbacks approach, it's very simple to deal with it from the languages like C++ or JavaScript, because for instance in C++ you can just use one of the vector constructors to copy the values that are provided by Rust. And it's very straightforward. You just copy the value and you can deal with it in any imaginable way afterwards, and you will be memory safe. And for JavaScript, it's even simpler because you have an implicit copy of value when you construct an array. So you just don't need to do much to make it work. And also a big advantage of this callbacks approach is that you get the asynchronous code working for free and without any changes. Because we can use features in our Rust code, and the external interface will be transparent for the end user because interface will be based on the very same callbacks convention. And we have successfully used this approach in our project, which largely depends on Tokyo and futures for input and output and the network communication. And it works really well for us. So to summarize, borrowing and ownership is a very complicated topic, and if we apply it to FFI, like it's a complicated topic in and of itself in Rust, like a lot of people struggled with it when they learned Rust, and it's even more complicated if we apply it to FFI. And again, there is no single proper way to deal with FFI at all. You have to find your own way, and you have to balance the approaches for your particular application. But at MadeSafe, we have found that generally borrowing is much more simpler than dealing with ownership and borrowing. Because with ownership transfer, we are making our user responsible for all memory blocks. And it is especially hard in JavaScript and other garbage collected languages because you can't control the memory allocation in a straightforward way. You have to deal with black magic to make it work properly. So in practice, we use a combined approach. For heavy binary object, we use a combination of Opaque pointers and ownership transfer. And for the rest of simple functions, callbacks work really well for us. And there are links to the FFI utility library that we use. It contains many useful utils for projects that follow this convention. And there is also a link to our Rust project that exposes the FFI interface in the way that I have described. And you can look at our implementation for an example of an API that is structured around callbacks. And that's basically it. I'm ready to answer your questions if you have any.